Welcome back. Today we're going to talk about what significance tests are. What are we actually trying to accomplish and how do we do it? How do we test for significance? So basically what we're doing with a significance test is we are testing a claim. So someone says 35% of Americans do XYZ, right? 35% of Americans watch a certain show on Netflix. So a significance test is going to help us formulate a couple hypotheses, either they do or they don't, test the claim, examine the results, and figure out, is this claim actually true, or is there reason for us to investigate it? So what does it look like? Well, first of all, anytime there's a claim, it's really a hypothesis. So let's take that example that we had. 35% of Americans watch a certain show on Netflix. Well, we form a hypothesis. And so at first we're going to say, what if that's true? Because one of two things could happen. Either it's true or it's not. And so in our minds, we should say, here's the claim. 35% of Americans watch this show. But your buddy, he's over there and he says, I think it's way less than that. See, now we actually have two hypotheses, right? One is 35% of Americans watch this show. But your buddy's got this alternative hypothesis that's, no, actually less than 35% of Americans watch this show. So what we do is then we test. We find out a way, however we do it, to test whether 35% of Americans actually watch this show. And then we either confirm my hypothesis or the claim that there's 35%, or it's less, or I guess it could be more in this case. But no matter how we slice it for these problems, we have to come up with this alternative hypothesis that says either it's less than, or it's not equal to, or it's more than, and compare that to what the claim was of 35%, or whatever the statistic happens to be. So we've got to get some vocabulary down here. The first thing we're going to talk about, and we sort of just touched on it, is the notion of hypotheses. And any claim from a problem, for example, down here we're going to talk about this calcium problem where calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers are not getting enough calcium on average. Is this true? So what's the claim? The claim is that we need to have this 1,300 milligrams. And so the claim as stated is called the null hypothesis. And we're going to notate that H sub 0, null, nothing, okay? Right? So it's either of a mean or it's of a proportion, right? So the claim is that 35% of Americans, that's a proportion. The claim is that the mean number of people in Ohio, whatever it is, the mean number of people in a state, I don't know. Okay, so this is going to be, is equal to the null value. This is where we put down what the claim is actually from the problem. So in this case, the null hypothesis down here would be H sub 0 is calcium intake is 1,300 milligrams. Okay. The other one, like I said in that problem with Netflix, is called the alternative hypothesis. And we're going to notate that H sub A, because it's the alternative hypothesis, and it's going to be either our mean or our proportion. And we can, based on the problem, we determine, is it less than, is it greater than, or at the very least, is it not equal to? And then we're going to set it up with the null value, right? Because what we're ultimately trying to test is the null hypothesis, the claim, that proportion, that mean, true, or is it something else? Now, you pick this on the content of the problem. Problem content. So for example, down here, what we're talking about is people think they're getting less than. So we'd make our alternative claim that it's less than 1,300, okay? So then what happens is we find a p-value. And this is going to look familiar. All right, so our p-value is the probability of getting the results or more extreme purely by chance. If the null is true. Okay, that is the key piece here. So when we test this claim, okay, this is where we're deciding when I do my experiment and I'm testing this hypothesis, and we've done this year, right? And it happens 3% of the time, purely by chance, okay? That's when we're evaluating that alpha value to say, well, it's less than 5%, so is it by chance? Is it not by chance? We're looking at those values, we're comparing them, and we're saying, could this have happened purely by chance? But we are assuming and testing it against the null hypothesis being true, whether or not you believe it. So if you don't believe that 35% of these people watch this Netflix show, that's okay. The claim from the problem, the claim from the prompt is that 35%. So how do we write conclusions? So first of all, we set up our hypotheses. Boom. Null hypothesis is this, alternative is this. Then we test. Now we have to make our conclusion based on results. So conclusions. This is how we write it. We do or do not have convincing evidence against the null. Our alpha value is our significance level. And we're going to evaluate our significance level versus our p-value. If our p-value is less than our alpha, that means it's significant. Let me give you an example. So let's say I've got that claim, that 35% claim, and I find a way to test this hypothesis. So I go in and I do an experiment. And I've got this whole, and this is where we would formulate a distribution, right? So we'd ask all kinds of samples. We do a sampling distribution. And we'd test all kinds of people, right, purely on chance, that 35% was true. And then I say, okay, 3% of the time, 3% of the time, there was 35% or more watched the Netflix show. However I tested. It's less than that 5% threshold that we've been using. And so that's significant. So that would make me think that's not happening purely by chance. Right? Not happening purely by chance. So if my p-value is less than that 5% threshold that we've been using, we could set it at whatever we want, but the 5%, then it's significant. Right? So if the 35% is happening less than 5% of the time, that's significant. Okay? Hopefully that made sense. I think I said it right. Let's rewind it. But if it happens less than 5% of the time, that's significant to say it's not happening purely by chance. Okay. All right, so let's look at an example. We're going to write a couple null hypotheses and test a claim. Calcium is a vital nutrient for health in bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The National Institute of Health is concerned that teenagers are not getting enough calcium on average. So 1,300 is our line. So we want to state the appropriate hypotheses, so this means 2, for performing a significance test. Be sure to define the parameter of interest. So this is 2 parts. So my H sub 0, my null hypothesis, is that my mean is equal to 1,300. My alternative hypothesis. Now up here, what I said was we've got 3 options, right? Either less than, equal, less than, greater than, or not equal to. We have to look at the context of the problem. So what is it that they are concerned about? They are concerned that they're not getting enough, which means they think that it is less than 1,300. Okay? But this alone by itself, if I didn't have the problem, wouldn't tell me any information at all, right? It just tells me some mean is 1,300. Is it 1,300 meters, $1,300? So I have to say that U equals true mean daily calcium intake for teens in milligrams. Okay, so here's my claim. Either it is 1,300 or it's less than. That's what we're testing. So they do this experiment. They ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each student. Data analysis reveals that the mean of this sample, so the sample mean X bar, is 1,198 milligrams, and the standard deviation is 411 milligrams. Researchers performed a significance test and obtained a p-value of 0.1404, which means they found that this p-value of 0.1404 is the probability that this would happen by chance. Okay, so explain what it would mean for the null hypothesis to be true. If the null hypothesis is true, the mean daily intake of calcium in the population of teens is 1,300 milligrams. Okay, so if the null hypothesis is true, that's what it is. So if I interpret the p-value, so what we're going to do is we're going to assume the mean daily intake is 1,300 milligrams. But Mr. Sayers, I thought we were testing that claim. Yes, but this is what we did with sampling distributions, right? So we assume that the 1,300 milligrams is true, and we run this experiment. And what we find is, what is the probability of it actually being 1,300 milligrams? Does that make sense? So we assume that it's 1,300, and we run the test as if it is 1,300 milligrams. So then what that tells us is, on the back end, when we're interpreting our results, we're seeing, well, if we assumed that it was 1,300, and we've got this probability distribution, right? How often did that happen by chance? That's the key right there. So we assumed that it was true. How often did it happen by chance? And so what we find is there is a 0.1404 probability of getting a sample mean of 1,198 milligrams purely by chance. And that's what happened up here, right? So what they did was they obtained the p-value for that 1,198. 14% was the probability on that.
At this time, all seniors traveling to the Bush Museum.
And so what I should note here is of 1,198 or less, purely by chance. So what conclusion should we make? Because the p-value is 0.1404.
Students.
So because it's 0.1404, we're comparing it to a 5% level. So what we're saying is 1,198 happened 14% of the time, which means that purely by chance, it came up 14% of the time. So that is greater than alpha. That's not alpha, that's alpha, which was 0.05, which means that we fail to reject our null hypothesis. Why? Well, think about it like this. If I have this claim here, I test it. 14% of the time, I happen to be less than the 1300. Okay, so purely by chance. It just so happened that 14% of the time, randomly, I got less than 1300. I'm not that concerned if I get something less than 1300 because it happened 14% of the time. So what I'm saying is the null hypothesis, then we don't reject it because that happens fairly often, 14% of the time. Now, what would be the alternative to this? Let's say I had this group of students. Their mean was 1,198. I ran this test. And in the test, 1% of the time, it was less than 1,300. Or sorry, it was 1,198. So 1% of the time in my test, where 1,300 was the true mean, 1% of the time, it was 1,198 or less. What I would do is I'd say, so you're telling me I just happened to pick a group of 20 teens that had this very low probability number? Not happening. No. That would make me reject it that it's 1,300. That would make me think it's not just this group of students. There's something going on here. Does that make sense? So the way that we say it is kind of confusing. We fail to reject H sub 0 because I'm not able to say, oh yeah, well, no, 1,300 can't possibly be it. Because what I'm saying is 14% of the time, it was 1,198 or less. Now you may think that's kind of a low number. Well, what we said is the significance level at 0.05 because it's 5%. So we fail to reject H sub 0. We don't have convincing evidence. Against the null. Does that make sense? So when I run these tests, I'm struggling. I want to make sure you guys got it. We run this test, and purely by chance, it happens very, very, very faint, very, very few times. That would make us go, no, that can't be true. But if it happens fairly often by chance, and we're going, yeah, that could be true. That could happen. I didn't just have a bad sample. This is true. Not a bad sample, but a more representative sample, right? So kind of keep that in mind as you're thinking about these things. All right, so now, whenever we're testing a hypothesis, so we've got this null hypothesis, and then we do the simulation or the experiment, we come up with our conclusion. You could get it right, okay? But oftentimes when we're interpreting this, there's an error that can happen. And so we're going to evaluate type 1 and type 2 errors. Here's basically how it works. The null hypothesis is what it is. So we take that 35% Netflix thing. So let's say that's our null hypothesis, and we anticipate that it's under. So that's our alternative hypothesis. So let's say we conclude that it's true, but it's not. Okay, so we would conclude that the null hypothesis is true, but it really wasn't. That would be one type of error. The other type of error is that the alternative hypothesis is true, but it's not. Okay, but we make the wrong decision. So we can make the wrong decision on either way. So let me outline it like this. Type 1 error. Okay, the null hypothesis is true, but we make the wrong decision. A type 2 error The alternative hypothesis is correct. Or is true, but we make the wrong decision. Okay. So the general outline for this up here would be like occurs by chance. Alpha percent, right? So that's where we're making that conclusion based on our alpha percent. So let's look at a specific example that can help us understand like what the types of errors are. So here's a straightforward example. Manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on the store records, the proportion of customers who had to wait longer than 2 minutes was P is equal to 0.63. To reduce this proportion, the manager assigns an additional employee to drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that our p-hat, so our proportion of this sample, is 144 out of 250, which is 0.576. So the manager then performs a test of the following hypothesis with a significance level of 10. So here we're changing our significance level, so keep that in mind as we evaluate these hypotheses. So the null hypothesis would be that 63% is true. That 0.63 probability is true. So that's our null hypothesis. But the manager, based on his results, found that his results were less. So our alternative hypothesis would be that our proportion is less than 0.63. Okay, so we've defined the hypotheses, and here's the explanation. So P is the true proportion of drive-through customers who have to wait longer than 2 minutes to receive their food. So it says describe a type 1 and a type 2 error. So, a type 1 error would be this. The null hypothesis is actually true, but we make the wrong decision. So the null hypothesis being true would mean this: 63% of customers wait longer than 2 minutes. But we make the wrong decision. So we would say, but the manager thinks less than that do. Okay? A type 2 error would be the alternative is actually true, but we think that it's not. We make the wrong decision. So the type 2 error would be actually less than 63%. Wait longer than 2 minutes. But the manager thinks it's 63%. Okay, so notice, hypothesis, null hypothesis is true, but we make the decision that the alternative is true. Or type 2, the alternative is actually true, but we think that the null is true. So which type of error is more serious in this case? So let's think about it for a second. If 63% of the customers wait longer than 2 minutes, but the manager thinks less than that do, that would mean he's saying 60% of our customers wait longer than 2 minutes. Nah, that can't be true. Or the manager comes out and says, listen, 63% of our customers are waiting 2 minutes. We need to do something about this. So which one's more serious? So in this case, the type 1 would be more serious. Why? Because the manager would be assuming that 63, okay, the manager is assuming that less than 63% of these people are waiting. So he's downplaying the severity of this. Does that make sense? So actually, it's the true proportion that's waiting is up here. But he's like, nah, we're good. As opposed to saying, man, this is how many, we have to get it down. Ours is up here, we got to get it down. Okay, so type 1, because the manager believes the extra employee reduces the proportion of customers who wait, but it does not. Okay, so it was at 63%. And he comes out and says, nah, we're really down here. Well, that would mean that he was wrong, right? So he put this extra employee on there, and now all of a sudden, it's not actually helping. Okay, so based on the question, the answer to question 2, do you agree with the company's choice of an alpha level of 0.10? Why or why not? So what do we have? So let's look at alpha level, significance level of 0.10. So no, we shouldn't do this. Because if the null is true, then an alpha level of 10% will result in a type 1 error 10% of the time. Okay, so they should use a smaller value because we don't want it to be that high that this could occur just by chance. So they should use a smaller alpha value. The p-value of the manager's test is 0.0385. Interpret the p-value. So if we assume that the proportion of customers who have to wait is 0.63, okay, so we assume that that is true. So we assume who wait is 0.63. There is a 0.0385 chance probability of getting a sample proportion of 0.576 or less purely by chance. Okay, so what does this mean? So we've got this fairly low p-value, which means that there is a low chance of getting it purely by chance. So what would that mean? Well, that would mean that we're on high alert here. We should think to ourselves, either we're on high alert here and we should think to ourselves, well, this raises a red flag, or if it's low enough, it's not. So that's where our alpha value comes in. So as we're comparing this to our alpha value, we put it at that 0.10. So this is our number 3. If the null is true, then an alpha value of 0.10, I'm popping back up here, will result in a type 1 error 10% of the time. just by chance. So they should use a smaller alpha value. That's why we put alpha at this lower level, because we want to be able to catch the fact that we have a type 1 error in a case like this more often, because we don't want to make that mistake and falsely assume that in this case, like putting this extra person on lowers our time of waiting, okay? So that's type 1 versus type 2 error. Got to have those straight in your mind, because as we move through these sections and we start to talk about the types of errors, the tail tests, and those sorts of things, we've got to have a good handle on what a type 1 and type 2 error is. Okay, guys, thanks for watching, and we'll see you next time.